Okay, so now I want to do a couple examples with electric field problems, just because those are a little bit trickier, but once you actually get the hang of it, there's not much more to it than we had when we were dealing with electric forces. So imagine you have a ping pong ball, and it has extra 7 microcoulombs of charge, and you put it in a region that has an electric field that has an upward direction and a magnitude of 5,000 newtons per coulomb. So in that region, you have that upward electric field, and then you put that 7 microcoulomb charge onto that ping pong ball, and it causes it to float. So the questions are, what is its mass, and is the charge positive or negative? So take a second and kind of see if you can set up this problem, and I'm going to provide the solutions going forward. So you can pause the video or just kind of watch and think as you go through. So as we always do, start with a free body diagram. So if we look at it, there have to be two different forces acting on it. We know it has weight. Need to change that to F's, the different values that we use there, but the weight is pulling it down, and then the electric field has to be pushing it up because it's floating. That's the only way for that to happen. And the only way for it to float is if those two forces are equal. So I look at the information that I'm given, and I know that the charge is 7 times 10 to the minus 6 coulombs. I don't know if that's positive or negative, but I'm just going to use that value for now. And then the electric field is 5,000 newtons per coulomb. So if I look at what my equations are going to be, I can say that the electric force upwards, which is equal to Q times the electric field, is equal to the gravitational field pulling down on it, mg. And if those two things are equal, I can solve for the mass. So that's QE over mg, and when I plug that in, I get 0.0036 kilograms, or 3.6 grams, which is a reasonable answer for the mass of a ping pong ball. It's in the right range. It's nice because those are the numbers I just made up, and then I checked to see if it worked, and it worked out. It doesn't always happen that way. Sometimes I solve it and say, wow, that is an 8-pound ping pong ball. Maybe I'll change it to a bowling ball. But it didn't quite work that way this time, and it actually came up the correct way. So if we look at that, we have the electric force, which is just the electric field acting on the charge, very similar to the gravitational field acting on a mass. But the only thing that I haven't answered up here, actually I have to listen for, sorry about that, is that the charge for the electric force to be in the same direction as the electric field, that means it's a positive charge, because positive charges follow electric fields. If the electric field was down and the force was up, you would need that negative charge to flip the direction around. I think that makes reasonable sense there. So like a proton would follow the electric field lines, but an electron would go in the opposite direction because it is negatively charged. All right, so here's a situation where you have two charges. You have a negative 5 microcoulomb charge at x equals 2 and a negative 7 microcoulomb charge placed at y equals 2. And we want to figure out what is the magnitude of the electric field at the origin and in what direction does it point. So to do that, now we're looking at electric fields created by point charges. That's where we use the kq over r squared relationship. And so we look at that, and because they're both negative charges, the electric field lines point toward those charges. I just called them QB and QC because we used QB and QC for the previous problem that I did the example with. So in that case, you have those forces, those electric fields, and they're both pointing toward the charges from that point at the origin. So there's our point of interest is the origin of these charges. So then I look at all of these variables, and we know that we have two negative charges, and then the two distances are the same. So if I look at that, I realize that I have one x component and one y component, where it's k, q over r squared. And so the electric field values are actually much higher than we had for the electric forces because the charges are so small. But we only have one charge to deal with in this case. So we plug that in, and when I find the field from charge B, it's 11,250 newtons per coulomb. When I plug that in for charge C, I get 15,750 newtons per coulomb. And then if those are our two vectors, so we go back to it, so our vectors are going to be, our y component is going to be the 15,750, and then the x component is going to be our 11,250. So then we can just set up a right triangle once again. So with that, take our x component is our x side of our triangle, y component is the y side of our triangle. Find the magnitude of the electric field. Magnitude, remember, just means the value of the hypotenuse, essentially. And so we put those together, and we get about 19,355 newtons per coulomb. And then if we plug in the angle, you get the same angle we got on that previous problem of 54.5 degrees. So these are two example problems that hopefully help you figure out what's going on in some of the practice problems.